Today we're going to look at a particular type of reaction called redox reaction. So topic 11 focuses on redox reactions, reduction and oxidation reactions. These are reactions that involve transfer of electrons between one species and another. And we've hinted at it before when we looked at some chemical reactions and balanced ionic equations. So I want to look at it in a little bit more depth this time round. I want to answer the question, what is oxidation, what is reduction? I want to introduce something called oxidation numbers, which is, sometimes it's called a chemical accounting. It is a way that we can use to aid balancing redox equations. And that is actually really quite difficult. So conceptually, some of this lecture, this topic, is really quite tricky, but we'll work through it slowly, and I hope you'll stay with me for that. What I want to do first off is just recap very briefly stoichiometry in terms of a few dot points. The essential equations that we saw yesterday and that you will use throughout chemistry is an amount, by which we mean numbers of moles. The amount of a substance is the mass of the substance in grams divided by the molar mass of that substance, which we look up on the periodic table. So really, really super important equation. When we're dealing with solutions and want to find out the concentration or the molarity of the solution, then the concentration is defined as the number of moles of the solute divided by the volume in litres. Concentrations are always given then in moles per litre, shortened to capital M for the units. So those are the two super important equations that we looked at and used yesterday. Stoichiometry, the whole field of stoichiometry is using this mole information in order to determine something about the reactions we're doing, in order to determine the amount of product we're going to get given the amount of starting material, or maybe the amount of starting materials I need to take in order to get us so much product. It's all about either chemical reactions, solids, liquids and gases, or in solutions. In both cases, we use the same broad method for approaching the problem. You start off with a balanced equation. That's essential. You need the correct formulas, and you need to correctly balance the equation for the reaction you're interested in. You need to determine the numbers of moles, given the information that you've got. Maybe it's a concentration in volume, maybe it's a mass. The next stage is determining numbers of moles. You then use the number of moles that you've determined for what you know, plus the balance equation, in order to get the number of moles for what you don't know, your aiming point in the calculation. So you convert to moles of unknown, and then from that you calculate the mass of the unknown, or maybe the volume of the unknown solution, or maybe the concentration of the unknown solution. So the four broad steps: balance equation, determine the number of moles, convert from moles you know to moles you don't know, convert back to the quantity that you want to know: mass, volume, even concentration. Okay. What I'd like to look at now is oxidation and reduction reactions. And our early concepts of oxidation involve reactions with oxygen. And just as a straightforward example, carbon burning in oxygen to give carbon dioxide. And we can see there's a whole suite of reactions of a similar sort. Let's give another example, say hydrogen burning in oxygen to give water, And if I was to balance that up, I need to add 2's in those positions. And this is what we call an oxidation reaction. It involves oxygen. But then if we look a little bit more deeply, there are many other reactions which are of the similar type that don't necessarily involve oxygen. For example, hydrogen might react with chlorine, in fact does react, not might react, to give hydrogen chloride gas. And if I was to balance that up, then the balance equation would look like that. And it's a similar sort of equation in as much that we're going from elements and forming a compound. And we find that this is a characteristic theme in all oxidation reactions, going from elements, forming a compound. Of course, the reverse can also work. If I take, for example, a copper oxide or, say, CuO and react it with carbon in a sort of smelting reaction or refining reaction, I can get from this copper and carbon dioxide. I need to balance this up a little bit, so I need 2 oxygens there, I need 2 oxygens there, and that means I end up with 2 coppers there. And from the point of view of what's happening to copper, I'm now going from a compound to an element. So this is the reverse of an oxidation reaction, and we call it a reduction reaction. And if I look at what's happening to carbon, it is similar to the top case where I go from elemental carbon to carbon dioxide. So that is what we've already defined as an oxidation. We're now seeing a compound to an element as a reduction, and overall then I have an oxidation reduction pair in this reaction, and we call it a redox reaction. And what we'll find is that reduction always occurs at the same time as oxidation, and vice versa. Let me remind you of a reaction that we did earlier where I took just some magnesium and added acid. We don't need these elements anymore. We're done with elements. I'm not going to test you on any other elements. We've run out of them. However, no, I promise not to. Magnesium, hydrochloric acid. An active metal like magnesium will react with any acid to give bubbles. Those bubbles are bubbles of hydrogen gas, flammable gas. If I add, it's quite hot there, if I add enough acid, I will dissolve all of that magnesium and end up with magnesium ions in solution. The overall reaction we saw when we looked at types of reaction was an active metal reacting with an acid to give them metal ions and hydrogen gas. And if I were to write this out, again, I could imagine we have magnesium and H+, the active components of acid, giving magnesium 2+ and hydrogen gas. Balancing this up, I need a 2 there, and with any equation involving charges, I need to balance with types of atoms, numbers of each type, and then check that the charges balance left and right, and they do. If I were to dissolve the magnesium completely, and if I were to use, say, hydrochloric acid, The spectator ion in the top case is chloride, so that evaporation of the water from the solution I get would give me magnesium chloride. And overall, I might write a formula equation for this, something like magnesium chloride plus hydrogen. And once again, I've got a situation where I've gone from an element to a compound, an oxidation reaction, and a situation where I've gone from a compound to an element, at least in terms of what's happening to the hydrogen. So a reduction type reaction. And what I can do is tease this reaction apart a little bit to focus in on just the oxidation bit, and that is what's happening to the magnesium. The magnesium is ending up as magnesium 2 plus by loss of electrons. And in fact, the magnesium has lost 2 electrons. And of course, that's what you expect from its position in group 2 of the periodic table. Moreover, if I think about what's happening to the hydrogen, I could write the H plus ending up as hydrogen gas. And if I think about what's happening here, H plus has no electrons associated with it at all. Hydrogen in an H2 molecule has 2 electrons associated with it. So from somewhere, the H plus must have gained 2 electrons. Where have they come from? Well, they've come from the magnesium bit. So these are what we call half equations. They focus on just the bit of the reaction which is the oxidation, and a half equation which shows an oxidation is one in which there is release of electrons on the right-hand side, and a half equation which shows reduction is where the electrons on the left-hand side, a reactant-like position, and are absorbed by the other species there to form the product. Our definition then is, in oxidation, we have loss of electrons. In reduction, we have gain of electrons. And this is where our mnemonic oil rig comes in. Oxidation is loss of electrons, reduction is gain of electrons. Oil rig. So, 2 half equations, and if I were to add them together, then I'd get the overall ionic equation that I have at the top there. Let me quickly do that. Let me, at this instance, keep in the electrons, but I find that I have the same number of electrons on both sides of the arrow, so I can cancel them out. And indeed, when I balance a redox reaction, I need to be able to do that so there's not a surplus or a deficit of electrons anywhere. And I'm back to the equation we saw. Active metal plus acid gives the metal ions plus hydrogen. But I've dissected that equation to see what's going on. Half equations can be treated like other equations in terms of charge. We have to balance for the type of element on each side, the number of each type of element, and then look at the overall charge. Overall no charge here, overall no charge there. So half equations, if properly balanced, have no overall charge difference between the left and the right-hand sides. Okay, well, there's a whole range of equations that are these redox type equations. And there's a list of them, or a list of some of them, at the bottom of page 2, and I just want to highlight perhaps one of them and show you what's happening. So, for example, the second one of the list is 2 lots of sodium reacting with bromine liquid giving sodium bromide. So I can see that I'm going from elements to compound. So from what I've said before, that sounds like an oxidation. But I've also said that whenever you have an oxidation, you also have a reduction. And I might wonder, where is the reduction in this? We can determine that if we write out the half equations. In terms of what's happening to sodium, I'm starting with the metal on the left, the element, no charge. In sodium bromide, the sodium ends up with a 1+ charge. That is what I expect. That's the magnitude of the charge of the cation, and hence 1 electron must have been given out. Now if I look at what's happening to the bromine in sodium bromide is the anion, Br-, and in order to get to the Br-, I have to add in an electron to the bromine. I need to balance up this half equation. I need another bromine on the right-hand side. I need to ensure that my equation is balanced for type of atom, for number of each type, and for overall charge. Overall, there's a 2- charge on the right. I need a 2- charge on the left to balance that up. So Br2 absorbing 2 electrons gives me 2 bromide anions. Well, if I add these two together, what will happen? You might be able to see that the electrons, as I've written them, these are 2 balanced half equations, but if I add them together, the electrons won't cancel out because I haven't got enough of them on the right-hand side from the top equation. So, if I am faced with a complicated example, and I'll show you one in a moment, I dissect the equation into the half equations, decide which is the oxidation and which is the reduction half equation. I need to balance the half equations so the electrons cancel. And overall, that means I've got to double the top equation. If I double everything on the top equation and add it to the bottom equation, I will end up with 2 lots of sodium plus 1 lot of Br2 plus the 2 electrons, giving 2 lots of Na plus 2 lots of E minus plus 2 lots of Br minus. The electrons now cancel with one another, and overall I've got sodium plus bromine giving 2 lots of sodium bromide. Depending on the conditions, I might have this as a solid, as in the top equation. I might perhaps imagine that I have this as a solution, as in the bottom equation. Okay, let me show you another reaction, and in fact I might need this screen for this. In all redox reactions. I can, if I arrange things carefully, separate out the two half equations. And when I separate out the two half equations, I can run the electrons through an external wire and end up with a battery. Now, what I'm going to do, what I've got here is a lemon. Quite a big lemon, but it doesn't have to be a big lemon, but it's a lemon. And what I'm going to do is put into my lemon a strip of zinc, and actually I don't really need my safety glasses on for that, and a strip of copper, so that they don't touch in the lemon. And now if I connect them up to my voltmeter, see that? Okay. And what do I have? I've got nearly a volt. Oops. Getting nearly a volt. 0.997, 0.998 of a volt out of my lemon. This is a battery. A redox reaction is occurring. The zinc is going to zinc 2 plus ions, and we're actually using the acid in the lemon to go from H plus ions to hydrogen gas. I won't light a match near it. So, redox reactions can be really important because they can enable us to use the electrons as they go from one part of the reaction cell to another, and we can use those to drive a light or a motor, something like that. Let me show you another battery, and for this one I do need a lab coat. It's actually a dry cell battery. It's the AA or AAA batteries that you can buy and use in many applications. Now, it's called a dry cell battery, but it's anything but, really, or at least the way I make it. It's not Actually, I probably don't need that one. Okay. What we need is an electrode, in this case a bit of zinc. This will be the casing of the battery. I need a chemical reaction. The chemical reaction will involve, in one part, the zinc going to zinc 2 plus ions. In another part, it'll involve manganese. I've got a compound of manganese there. I need something to conduct the ions within the battery, but keep the parts of the reacting species apart. So I've got a bit of sponge here, which I've soaked in a material called ammonium chloride. I'm going to add my magnesium compound into the middle of this sponge. I'm going to now add my electrode, which will pick up the charge, and it even looks like a AA battery, don't you think? And attach that together, and there's my dry cell. A little bit messy. Let me see what voltage we can get from it. So here we go. One and a half volts. Isn't that fantastic? So there is my dry cell battery, my A battery, that's for Adrian battery, generating 1.5 volts. And in fact, the type of the reaction it is will determine the voltage that you get from the battery. So that the lead acid batteries in the cars, each cell there has capacity to generate 2 volts because of the chemical reaction that's involved. AA battery, AAA battery is always 1.5 volts. One of the smaller nickel cadmium batteries, that's potentially a different voltage that you get out from the battery. So the charge, the voltage that you get out is actually unique to the chemical reaction. Okay, well, a bit more on redox stuff. We're looking at reactions in which electrons are transferred. We can use this for our own benefit if we arrange the chemical reaction in a way that we separate out the reacting species, the chemically reacting species, but allow electrons to transfer around an external wire from one reacting species to another reacting species. Now, what I want to show you is the worst case scenario for these redox reactions. It is actually a hideous looking reaction. In fact, I think it needs a entirely new set of boards here. It is a reaction starting with iron 2+, reacting it with another manganese compound, MnO4-. We actually happen to need some H+ present as well, and this equation is page 3, so don't copy it down. I end up with iron 3+ as a product. I end up with manganese 2+ as a product, and I end up with water. Now, this isn't balanced at this stage. It's slightly different from the one in the book at this stage. If I look at it, I've got the same types of atoms on both sides of the arrow. I've got the same number of each type of atom. But if I look at the overall charge, I've got 8 pluses, 1 minus, that's 7 plus, and 2 pluses means I've got 9 plus on the left, and I've only got 5 plus on the right. So something's wrong there. Now, if I jump to the answer that's in the book, you'll see that I actually need 5 lots of iron on both sides of the equation. But it would actually, I think, be very difficult to arrive at that as a balanced equation. It should be balanced now in terms of charge. 5 times 2 is plus 10, plus 8, so that's 18, minus 1 is plus 17, and what have we got on the right? We've got 3 times 5 is plus 15, plus 16, plus 17. So it's now balanced for charge. But I'd say it's pretty much impossible to do that on its own. This is a really ugly redox reaction, but let us look at it in parts as to what's going on. Let's focus on the iron to start off with, and I can see that the iron 2+ goes to iron 3+. That's straightforward to understand in terms of loss of 1 electron, and hence this is the oxidation half cell, half reaction. Oxidation, half reaction. What about the rest? It's very difficult at this stage to be able to make any sense of it. H+ ends up as water. Well, we haven't got a situation where we've gone from an element to a compound or vice versa. And similarly, the oxygen of the manganese. We haven't got that sense either. It's a bit difficult because the manganese here is a polyatomic ion that's negatively charged, and over on the right-hand side, it's a single cation. What we need is something we call oxidation numbers in order to make sense of what's going on. And what I want to do is run through the rules for assigning oxidation numbers And these are on the top of page 5 of the booklet, and there's just 4 of them. I think it's page 5. Top of page. And there's 4 of them. Let me run through them and give you an example. The first one says that for simple cations, the oxidation number equals a charge. What do I mean by that? For a start, by simple cations, I mean ones that are just a single charged atom. Something like Na+, Mg2+. Not a polyatomic ion like NH4+. So the oxidation number is the same as the charge. Now, in order to distinguish an oxidation number from a charge, we always use, and this is really important, we always use Roman numerals. We indicate also a charge with it. So the oxidation number of an Na+ cation is +1. And in this way, there is no confusion with the valence of the element or with the charge that that element might have. So Roman numerals are essential. For magnesium 2+, it's +2. Rule 2 says that for simple anions, the oxidation number is also the charge. And giving a couple of examples, O2 minus, Cl minus. Once again, we're not looking at polyatomic anions, just simple anions where the oxidation number equals a charge. So O2 minus is an oxidation number -2, -1 for Cl minus. Rule 3 says for elements, i.e. uncharged atoms, the oxidation number equals 0. If we had just magnesium or just hydrogen, the oxidation number would be 0. And the fourth and final rule says that for a polyatomic ion, leave it a polyatomic ion. We find that the sum of the oxidation numbers equals the charge, and we also, and this is important, take oxygen as -2 and hydrogen as +1. So what we're looking at is whenever we have a molecule, I should really have said molecule or polyatomic ion, whenever we have a cluster of atoms bonded together as a molecule, if there's no charge, polyatomic ion, if there is a charge, if there's oxygen in that, we say that the oxidation number of the oxygen is -2. If there's hydrogen, it's +1. Beyond that, the sum of the oxidation numbers equals the charge. So, if I look at a neutral molecule like H2O, then oxidation number of oxygen is -2. The oxidation number of hydrogen is +1. 2 times +1 and -2 gives me no overall charge. So it's a neutral molecule. If I look at NH4+, Hydrogen is +1. There's 4 of them, so that contributes a total of +4. We don't know what nitrogen is. We want to find that out. But nitrogen, oxidation number +4 for the contribution of the hydrogens gives me a residual charge of +1. That means that nitrogen has got to be -3. So -3 +4 gives me +1. Now let me go back to our equation here. Oxidation number of a simple cation +2. In case of iron 2+, +3 for iron 3+. We've already decided this is an oxidation half equation, and we find that oxidation involves an increase in oxidation number, going from +2 to +3. What about the other species present? Let's assign oxidation numbers to everything. Well, let's do the easy bits first. H+ is oxidation number of +1. In a compound like water, hydrogen is +1, oxygen is -2. 2 times +1 is exactly balanced by the -2 of the oxygen, so no overall charge in water, as you'd expect. Simple anion like Mn2+ has an oxidation number of +2. Polyatomic ion like MnO4-, oxygen is -2. We've got 4 of those. We don't know what the oxidation number of manganese is. We want to determine that. We know that the overall charge is -1. So, the way I think about it is oxygen contributes -8. We've got -1 left over, therefore manganese must be +7. There's no way that we'll ever get a cation with a +7 charge on it. So oxidation numbers are not the same as the charge on a cation. Well, what we can now see a little bit more clearly is that the manganese is changing its oxidation state from +7 to +2. And that is going to be the reduction half reaction. MnO4- ending up as Mn2+. If I take my cue from the oxidation numbers, the number of electrons that are transferred relates to the change in oxidation number. If I've got an increase in oxidation number, it's an oxidation reaction. An increase of 1 unit gives me 1 electron. In this case, I've got a decrease from +7 to +2. So a decrease in oxidation number is going to be a reduction . The oxidation number has decreased by 5 units, so it's going to be a 5 electron reduction. I've now got to do something about balancing this up. Oxygen on the left but not on the right, and we see from the equation that water is involved, and I need 4 lots of H2O to use up the oxygens there. I've solved the oxygen problem, but I've introduced another problem, and that is hydrogen. I've got 8 lots of hydrogen on the right, and I need 8 lots of hydrogen and this reaction is done under acid conditions, not something I need anyone to know at this stage. So it's 8 lots of H plus on the left. The oxidation number of hydrogen doesn't change. The oxidation number of oxygen doesn't change. It's only the manganese that changes oxidation number. Now, having got correctly balanced half equations, and let me check the charges here, 8 plus and 5 minus, and another minus, so 8 plus and 6 minus gives me an overall 2 plus, and we've got an overall 2 plus there. So that's a balanced half equation, or half reaction. If I were to add these together, I need to do so in a way that the electrons cancel out. And the only way I can cancel out the electrons on the left here, the 5 electrons on the left, is by having 5 electrons on the right, and hence I multiply the whole of the top half equation by 5 to end up with my balanced equation, 5 times Fe2 plus MnO4 minus plus 5E minus plus 8H plus, giving 5 times Fe3 plus 5E minus plus manganese 2 plus and 4 lots of H2O, and the electrons balance out and I have a balanced redox equation. And it would be very, very difficult to do that balancing in any other way. So, to summarize this section, redox equations are really very common. They're ones in which electrons are transferred from one species to another. One way we can tackle this is to assign oxidation numbers to the atoms in the reactants and the atoms or ions in the products. If there is an increase in oxidation number, we class that as an oxidation. If there is a decrease in oxidation number, we class that as a reduction. In order to get a balanced equation, we need to make sure that the number of electrons produced in the oxidation half reaction exactly balance the number of electrons produced in the reduction half reaction. So there's no deficit or excess of electrons. The way we do that is by separating out the two half equations, balancing them for electrons, comparing them and making sure that we balance the electrons of one half equation with those of the other half equation. And what I want to do is finish by showing you another redox reaction. I'm not going to separate the two half equations in this case. I'm going to do it all in one reaction pot. So I could never make this into a battery. It's actually quite a complicated redox reaction. It involves actually a little bit more than 3 components. But what I get from it, I hope, is a bit of a change of colour. Certainly it's gone a nice sort of straw colour. I think that's darkening a little bit. You might just be able to see some dark colour appearing, and it goes nicely to blue, and will, if you happen to have missed it that time round, we can try it again and get rid of the blue colour, and there it is again. And if you're a bit slack and have missed it a second time, well, let's have another go at it and see how this can continue. And there we go again. And you can imagine, you could tell something about the speed of a reaction by measuring the oscillations, the appearance of that blue colour. And this will continue for a short time, but not forever. Okay, we'll leave it at that.